This is going to be a lesson about the unit circle. To explain the unit circle, let's start by drawing on an xy axis. Now on this axis, I'm going to draw a circle whose radius is exactly 1 unit. Now if we drew on a point with coordinates xy, we can draw a right-angled triangle beneath this point to help us find an equation for this circle. Now we know that the x-coordinate just gives us the distance from here to here, and the y-coordinate just gives us the distance from here to here. So let's go ahead and mark that on the triangle. Since we know that the radius of this circle is just 1, then we can mark that one too. Writing Pythagoras' theorem for this triangle allows us to find an expression that points on the triangle must obey. I can easily show you this. For example, this point over here does not lie on the edge of the circle. So when I sub it into the left-hand side of this expression, it's not going to equal 1, as I'll show you now. So when we sub this point into this equation, we saw that 0.04 squared plus 0.04 squared is actually 0.32, and that is not equal to the number 1. This point, however, looks like it is on the edge of the circle, so if we sub it in, it should equal 1. This time, the coordinate is 0.8 minus 0.6, and if we sub this in, we do get 1 this time, so this checks out. So basically, we can use Pythagoras to test whether points lie on the edge of a unit circle. Now, I'm going to hide all the information I don't need to introduce the trigonometric functions. Let's pretend for a moment that I had a laser pointing in the direction of the positive x-axis. Now suppose for the moment that I pointed this laser in the direction of the xy axis and I let it take a shot. Remember that we can mark this angle with a theta. But wouldn't it be great if we could take this theta and find the corresponding x and y for it? This is the goal of the trigonometric functions. I can easily draw these trigonometric functions as a pair of machines. The function that takes in theta and gives you the x-coordinate is called cosine, and the function that takes in theta and gives you the y-coordinate is called sine. So as you can see here, the x-coordinate is the same thing as cosine theta, and the y-coordinate is the same thing as sine theta. To show you how this works, let's turn the laser off for a minute and point it in another direction to find the sine and cosine of a particular angle. Now I've randomly chosen an angle of pi on 3 radians, and if we look carefully at the point where the laser hit the circle, we can actually go ahead and find its coordinates. Remembering that the x-coordinate is cos and the y-coordinate is sine, then we know the value of cos pi on 3 radians and sine pi on 3 radians. Cos pi on 3 radians is 0.5 and sine pi on 3 radians is 0.87. You can repeat this for absolutely any point on the circle that you like. Now for those of you that actually tried to type this into the calculator, you might have run into a little bit of a problem. What do you do with these radians over here? It turns out you don't type them in at all. You just type cos pi on 3. However, there is a slight problem. Anytime you use one of the trigonometric functions in your calculator, you have to make sure that your calculator is set to the right mode. In this particular case, I'm subbing in an angle in radians, so I have to make sure my calculator is set to radians. If you're unsure how to set your calculator to radians, I'm sure you can find a search engine that can help you out. But that's enough on the calculator for now. Now, I'm going to move the laser back to its original place so I can tell you about the last trigonometric function for today. The final trigonometric function I'm going to tell you about is going to find the gradient of this line right here. This final trigonometric function is called tan. Now we've always defined the gradient as rise over run. But for this point, the rise is just y, and the run is just x. Now just looking at this and all the values over here, we can immediately write the following relationship. This relationship is really just saying that m equals y on x, which we knew already. Now there is actually a really cool way to visualize the tan of theta, which I'll go ahead and show you now. I want you to see that we stretched this little triangle into this bigger triangle. When we did this stretch, this cos theta turned into a 1, and we did that by dividing cos theta by cos theta, since anything divided by itself is 1. Since this side had to be divided by cos theta, then it also follows that this side also has to be divided by cos theta to get to this side. Now, as we already said, sine theta divided by cos theta is just the same thing as tan theta. That means this height over here is the exact same thing as the gradient. You can use this to help you visualize the gradient anywhere on the circle. As you can see, as the gradient gets very close to a right angle, this gradient is going to get very, very large. Once the angle is larger than a right angle, it turns out that the gradient is going to end up hitting down here. So you'll actually get a negative number. Now, speaking of negative numbers, there is actually one final thing to say about all of this. If we bring back the unit circle just for a moment, we're going to want to figure out when either cos, sine, or tan are either positive or negative. To do this, we're going to divide space into 4 regions called quadrants. We number these counterclockwise because, remember, that's the direction of a positive angle. Firstly, I'm going to highlight the 2 quadrants where the x-coordinate is positive. Now remember, since x is the same thing as cos theta, wherever x is greater than 0, then cos theta must also be greater than 0, and that happens in quadrant 1 and quadrant 4. Now I'm going to highlight all of the places where the sine of theta is positive as well. Now if we remember our shortcut for visualizing the gradient, remember that whenever it's in either one of these 2 quadrants, we are going to get a positive value. So let's go ahead and mark that as well. Now this is really all there is to say on the matter. If the angle you put in is in the first quadrant, then all 3 of the trig ratios must be positive. If it's in the second quadrant, then only sine is positive. If it's in the third quadrant, then only tan is positive. And if it's in the fourth quadrant, then you know only cos will be positive, and the other 2 will be negative. And with that, we've concluded our discussion on the unit circle.